Welcome back to my lectures on Galois theory. Our next topic is automorphisms on fields. Automorphisms. On fields. So we'll start with a definition. Let F be a field and alpha and beta are algebraic over F. Then alpha and beta are conjugates over F if the irreducible polynomial of alpha over F is equal to the irreducible polynomial of beta over F. We'll do some examples here. Examples. Let's take root 2 over Q. Root 2 is algebraic over Q. Suppose we want to find out the conjugate of root. See, when you say alpha and beta are conjugates over F, that means alpha is conjugate to B and beta is conjugate to alpha. So first of all, we need to find out the irreducible polynomial of root 2. That we already know. The irreducible polynomial of root 2 over Q is equal to x square minus 2. So the other conjugate has to have the same irreducible polynomial. So what are the zeros of this polynomial? The other zero of x square minus 2 is minus root 2. So root 2 and minus root 2 have same irreducible polynomials over Q. And that means root 2 and minus root 2 are conjugates over Q. Let us take another one. Let's take 3 plus root 2. So first thing we have to do is we need to find out the irreducible polynomial. So over Q. So that means irreducible polynomial of 3 plus root 2 over Q. What is that? That is how do you find it out? X equal to 3 plus root 2. So x minus 3 is equal to root 2. X minus 3 whole square is equal to 2. So x square minus 6x plus 9 minus 2 equal to 0. So x square minus 6x plus 7. So this is a polynomial. X square minus 6x plus 7, right? So the other root the other 0 of x square minus 6x plus 7 is what? It's going to be 3 minus root. You can find it out from here, minus b plus or minus root of 4, b square minus 4ac divided. So that is actually 3 minus root. So the conjugate of 3 plus root 2 over q is 3 minus root. Let us do one more. Let us take root 2 plus I over q. So the irreducible polynomial of root 2 plus I over q is what? X equal to root 2 plus I, x minus root 2 is equal to I. So x minus root 2 square is equal to 1. So x square minus 2 root 2 plus 2 minus 1 equal to 0. So x square minus, so this will be plus 1 is equal to 2 root 2, and that implies x square plus 1 whole square minus 8 is equal to 0. So I don't want to expand that. X square, if you want you can do it, but I'm not going to do it now. And the roots are, and the roots of these equations, or the zeros of x square plus 1 whole square minus 8 are root 2 plus I, root 2 minus I, minus root 2 plus I, and minus root 2 minus I. So the conjugates are of root 2 plus I are minus root 2 plus I, minus root 2 minus I, root 2 minus I. We'll do one more, which is a little bit different than this. Let's take 4, say root of 1 plus root 2. I'm going to do it over q root 2. Not just q, it's q root 2. So the polynomial is not actually over q. The polynomial, the irreducible polynomial is over q of root 2. So the irreducible polynomial of root of 1 plus root 2 over q root 2 is, root of 1 plus root 2 is equal to x. So x square is equal to 1 plus root 2. So the polynomial, you don't need to eliminate root 2 because you are trying to find the polynomial over q root 2. So this is actually x square minus 1 minus root 2. So the conjugate of root of 1 plus root 2 is just minus root of 1 plus root 2. the difference between these two examples are, this is, you are going to find the irreducible polynomial over Q, but here it is Q of root 2. If it would have been Q, then you will have 2 more elements here, because the polynomial will have, the irreducible polynomial is going to be 4th degree. Now that we defined the conjugates, conjugate elements of a field, the next step is to characterize the conjugates, meaning we are going to derive a necessary and sufficient condition for 2 elements or more than 2 elements, 2 or more elements to be conjugates. So let F be a field and alpha comma beta be algebraic over F. So what is a necessary and sufficient condition for alpha and beta to be conjugates? So since alpha and beta are algebraic over F, then F alpha and F beta are finite extensions of F. So the good way of finding out the necessary and sufficient condition is whether any kind of isomorphism exists between these two. If there is an isomorphism between these two, and then we can say that probably alpha and beta are conjugates. So the condition is that the map psi of alpha beta conjugate map from f of alpha to f of beta defined by f of alpha. Okay, so let us assume that, and degree of, I'm going to take degree of alpha over f is equal to n for some n. Defined by, so what are the elements of f of alpha? The elements of f of alpha are a0 plus a1 x plus dash a1 alpha dash dash a n minus 1 alpha to the power of n minus 1, where ai belongs to f, because the degree of alpha over f is n. So we are going to take one element from here and mapping an element here. So that is how we are going to define z of alpha comma beta over, instead of a, I'm going to use it c0 plus c1 alpha plus dash 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 cn minus 1 alpha to the power of n minus 1 is equal to, so this is definitely an element here. Is equal to c0 plus c1 beta plus dash dash c n minus 1 beta to the power of n minus 1. and this actually belongs to f of beta. We are not sure the degree of beta, but still definitely it is going to be inside this, because if it is less than this, then you can recompute the beta to the power of n's. See, alpha is an algebraic element over f of degree n. So we can assume one polynomial, irreducible polynomial of alpha over f. So let the irreducible polynomial of alpha over f, and suppose, before we going further, suppose this map, suppose psi alpha beta be an isomorphism. So there is a irreducible polynomial of alpha over f. Let it be a0 plus a1x plus dash dash an x to the power of n. Here it is n because the degree is n. ai for some ai's in f. So what does this mean? This means that a0 plus a1 alpha plus dash 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 an alpha to the power of n is equal to 0, because it is an irreducible polynomial of alpha over f. Right? So let us take the map of this on f of beta. So psi of alpha beta of a0 plus a1 alpha plus dash dash an alpha to the power of n is equal to this. We are assuming that it's an isomorphism, so we can write it as psi of, write it as what? It is write as a0 plus a1 beta plus dash dash an beta to the power of n. Right? And this is equal to 0. So we can write it as this is equal to 0 because the isomorphism mapping of a 0 element is 0 always. This 0 is from f of beta. So this is equal to 0. This is a polynomial in 0, in beta. So let us take this as a polynomial of p of beta. Okay, so p of beta is equal to 0. Okay, so we have a result earlier that if p of x is an irreducible polynomial of alpha over f, and f of x belongs to f of x such that f of alpha is equal to 0, so then p of x divides f of x. Because this is the smallest polynomial, meaning a polynomial of lowest degree satisfying p of alpha is equal to 0. If you take any other polynomial in f of x, then this is a factor of this. So here p of beta is equal to 0. So this implies that irreducible polynomial of beta over f, because this is going to be 0 when when you substitute x by beta, divides, this is our p of x here, and this is our f of x, divides irreducible polynomial of alpha over f. See, this is our p of x, and that is actually the reducible polynomial of. So irreducible polynomial of beta divides irreducible polynomial of alpha. With a similar argument, see, this is an isomorphism with so you can talk about inverse of alpha beta. So this is a isomorphism, so you can always, there's always a inverse axis. We can say that irreducible polynomial of alpha comma f divides irreducible polynomial of beta comma f. And irreducible polynomials are all mono polynomials, like the coefficient of the highest degree is always 1. So since the irreducible polynomials are mono or monic polynomial, monic, that implies what? That implies irreducible polynomial of alpha over f is equal to irreducible polynomial of beta over f. And what does that mean? That means alpha and beta are conjugates. So if we can define an isomorphism like this, this has to be an isomorphism. That is our assumption. If we can define an isomorphism like this, then alpha and beta are conjugates. So that is so that is a necessary condition. Okay. Now we will assume that if alpha and beta are conjugates, can we define an isomorphism like this? So now we are going to establish the sufficient condition. That means if alpha and beta are conjugates, then there exists an isomorphism from the simple extension of alpha to the simple extension of beta. So before we go there, I want to touch base with a result from ring homomorphism. So let phi be a homomorphism from R1 to R2 with kernel n. This is a homomorphism from R1 to R2 with the kernel n. Then there exists a isomorphism from isomorphism xi from R1, the factor ring R1 over n to the image of phi. This is a result we established earlier in ring homomorphism. So we are going to use it here because we need an existence of an isomorphism here. We are assuming that alpha and beta are conjugates, and we need to establish there exists an isomorphism, and that is where we are going to use this result. So alpha and beta are conjugates. Assume conjugates. So f alpha and f beta are finite extension of f. Right? So consider the evaluation map. Consider the evaluation maps. Evaluation homomorphism maps. What are the evaluation homomorphisms? Now let's call it as phi of alpha from f of x to f of alpha and phi of beta from f of x to f of beta. Just a reminder, the way you are defining this, phi of alpha of a polynomial of x is equal to the polynomial in alpha. That is how we define. Like that, phi of beta of p of x is equal to p of beta. So remind that. So we are going to use this result. That is how the evaluation map goes. So we have an f of x here, and we have an f of beta here, and we have an f of alpha here. This is our phi of alpha, this is phi of beta. Take a polynomial from here, replace x by beta, you get the element here. Take a polynomial from here, replace x by alpha, get the element here. So the kernel of phi of alpha, that is equal to the ideal generated by the irreducible polynomial of alpha over f. What is the definition of kernel? The elements from f of x that is mapped to a 0 of this. And of course, this will always map a 0 of this. And that is. And kernel of phi beta is equal to the ideal generated by the irreducible polynomial of beta over f. But alpha and beta are conjugates, meaning irreducible polynomial of alpha is equal to irreducible polynomial of beta over f. So that means kernel of phi of alpha is equal to kernel of phi of beta, and let it be n. So this is a homomorphism with the kernel n, and this is also a homomorphism with the kernel n. So we can always talk about an isomorphism from here to here and from here to here. Right? So there exists isomorphism from, let's call it as isomorphism, let's call it alpha, psi alpha from f of x over n to f of alpha, and psi of beta from f of x over n to f of beta. So because these two are isomorphisms, we can consider an inverse of, this is our setup B, a psi alpha, this is psi beta. So always psi alpha inverse exists because this is an isomorphism. So consider, we call it as psi of alpha beta as psi of beta after psi of, this is a composition of two maps starting from psi of inverse is starting from f of alpha and ends in f of x over n, and psi of beta takes it from f of x over n to f of beta. So this is an isomorphism from f of alpha to f of beta. So we established an isomorphism if they are conjugates. Now we need to find out the definition of this isomorphism. What is this isomorphism mapping from f of alpha to f of beta? So we'll take an element from here. So what are the elements of f of alpha? Psi of alpha beta. The element of f of alpha is c0 plus c1 alpha plus dash dash cn minus 1 x alpha to the power of n minus 1 equal to psi of beta of psi inverse alpha of z0 plus c1 alpha plus dash dash c n minus 1 alpha to the power of n minus 1. And what is this going to be? This is an element in f of x over n. So this has to be a polynomial. How do you get that polynomial? The definition goes like this. Psi of alpha is actually from here to here, some polynomial of x plus n is equal to p of alpha. That is how you are defining it. So when you take the inverse of this is a polynomial in alpha, then this will be c0 plus c1 alpha plus dash dash plus cn minus 1 alpha to the power of n minus 1 plus n, because that's the inverse. Of course, that is of psi of beta. And psi of beta, take a polynomial in n. This is actually coming from here, so it is going to be this is going to be x, because this is a element from f of x, because this is our p of x and this is n, and this is our p of alpha. So what does this mean? This means that psi of beta of c0 plus psi of beta of c1x plus dash dash dash, or you can say this is going to be, replace x by beta and take out this n. So that is going to be c0 plus c1 beta plus dash dash cn minus 1 beta to the power of n minus 1. And that is the definition we are looking for this isomorphism. So for two elements alpha and beta, if they are conjugates, there exists a isomorphism from f alpha to f beta defined by this z0 plus c1 alpha plus dash dash c1 n minus 1 alpha to the power of n is equal to this. So this is an isomorphism if alpha and beta are conjugates, and that is our sufficient condition.